Yo, today we're going to start development on Umi, the kind of new language that I'm thinking of. Now, Umi is actually the Japanese word for sea, which is exactly the wallpaper that you're seeing on the screen right now. So it's kind of a fitting name. So Umi means sea, and as you know, the C programming language has been a very important and historical language across the computer science and software engineering world. So I wanted to continue that legacy and kind of build off of it. And we'll see how this goes. For all I know, this project could end in complete failure. It could take off. It could do nothing and just be a really wonderful learning experience. To be sure, I'm not sure, but we're going to go ahead and we're going to start writing the compiler for this thing anyway. So let's get to it. The first thing I'm going to do is open up CLion, which is the editor that I use. If you're following my other project, then you can see we have that project folder right here. But I'm going to start a new project, and we're going to call it the UMI project, C++20. Let's go. So hopefully this is still displaying on the capture. But the very first thing that I'm going to do is I'm going to change the CMake default settings because I don't really understand why CLion always decides to put the default build directory to be this terrible, terrible name. I guess some people like it. Otherwise, they wouldn't have set that as a default. But personally, for me, I like to usually just stick everything underneath a build directory. And the rest of these settings are going to be fine. Use applecling as the compiler. Okay, get rid of you. Now, again, I'm not quite sure how much CMake is kind of general knowledge out there, but I usually like to use CMake 3.23 at the time of recording because it's not too old and not too new. And I guess if I go quickly through these commands, CMake minimum required is a command which basically tells CMake what the minimum CMake version is that you're expecting. And on this machine, we have CMake 4, which is one of the latest versions at the time of recording, but we're using CMake, which is slightly older than that. The next command, project, is the name of the project. Here, you can actually also put what languages you're expecting to use. And we're going to use C and CXX. CXX just means C++. And the next thing is that in CMake, there is this built-in variable called the CMake CXX standard. And by setting that to the number 20, then we activate C++20. And what that boils down to concretely is that when the compiler is, what is it? I think it's C++ stood or something. No, it's standard equals C++20. On the compiler's command line that CMake generates, this flag gets passed, or whatever the equivalent flag is for the specific compiler. For us, without a doubt, by reload the CMake project, you can't see it here because it happened behind the scenes. But if I just quickly delete the build directory and reconfigure, then you can see that actually it's not from configuration, it's if you build it. So if I build it, hopefully you can't see it here. But in the generated build system, that would be inside of, because we're using Ninja as the build tool, then the generated build system would be all inside of here. Somewhere there's going to be a stood flag. There it is. I guess GNU++ 20 is C++20 with GNU GCC style extensions. That's why it's GNU++ 20. But it's essentially the same thing. Flags is a set. Okay. Getting all the boilerplate out of the way, we're going to call this, I don't know, simple test. And what will be the simple test, you might wonder? What even will this language look like? Let me write a small file. So I'm going to call this thing main.umi. And to stick with classic C++ style naming, we're going to just create a very simple kind of hello world program. Actually, in doing that, I want to make a directory. We'll make this directory be called examples. And I'll stick this inside of there. And also inside of examples, I'm going to make what will become similar to a standard library one day, I suppose. To be honest, I'm not a fan of standard libraries, but I guess we can call this code that comes with the compiler. But for the time being, we'll just call it std. And the reason why I did that is because what I want to do is first, the way that you would import something in this language is we could just say import, and we'll just do this. Import std would just kind of like in Python, it would just make all of the names underneath std available to the calling code. I suppose an example would probably be the best way to explain that. So functions, there's a lot of different ways to make functions. In C++, you can say like order function, and then you have the parameters like an int, f, and then float. I guess I should have done something like this, right? Float f, int I, and then you can have the return type to be on the left side. That's kind of quote unquote modern C++. Or you can do the same function in traditional C style, which would be like this. Both of these things are fine, but the way that I want to do it is inspired by Kotlin. So what I want to do is I want to say that a function is introduced with the fun keyword like this, and then we'll call it main. That's kind of the minimal necessary function name that you need to have a working executable. And at the start, we'll have the typical C++, C++ parameters that start off a function. So we'll have like an argc, and we'll have a char array. This is one of the things that it's going to be new. It's going to be a char star array, actually, called argv, and this language will feature trailing return types. So this is meant to return an int, and then kind of similar, it's going to be like a braced language family. And what I want to do is I want to call std.print. And actually, what I would love to do is, now I'm not 100% decided on if I want like the standard print built-in print function to be called print or printf. I feel like because of muscle memory, I'm probably going to want to call it printf. But for the time being, I guess we'll call it printf. And then we'll just pass it a string literal, and we'll just give the classic hello world with \n. And then finally, we will return 0. And this will be the minimal working example for the time being. But of course, since we're importing from std, we actually need to have something underneath std. Now, with import statements, it's kind of, again, like Python, I want to be able to say the general package, or in this case, the folder, or I want to be able to grab something from inside of it. And I don't really need this to be like Python in that you need to have a special file, which would say whether or not this was a package or a module. Again, we're following the C++ way of doing things. So I'm actually going to want to say std, and then inside of here, we'll create another new file, and we'll call this, I'm not sure. I guess we'll call this ir.umi. So that way this reads quite nicely, and it will be std.io. And implicitly, this is like Python. Implicitly, every module will end in .umi as the canonical extension, but you don't need to specify the extension when you're importing stuff. Also, I should add that every file should specify its own namespace. So here, nothing kind of the same with every other modern language. This won't import everything or include everything like a C++ hash include statement. What this will do is it will just make the names available, but unless you use the names, for example, std.io. So if I'm following my own example, this should be std.io. Then this, because we're using the function name printf from std.io, to be honest, I'm actually not quite now I'm not 100% sure how I want to call this out. I could want this to actually just be std.io, in which case what I would do is simplify this a bit more, and we'd have it like this. And maybe this could just be called lib or std.lib, like this. In which case now, this would be known to the compiler, and then you just can import std.io directly, and then inside of std.io, we would have a function called printf that takes in a const char array, which is the format string. And then eventually we'll have variadic parameters, but it's not going to be naive like you would expect a C function to be. This will be fully typed. And to be honest, I'm thinking of making printf some kind of macro, but we'll see how that goes. There's a lot of things that, in doing this, actually, it's a lot of me sorting out what I've been thinking about this language for the last 2 years or so. So it's great that finally have the opportunity to do this, but we'll also put int here. Here we don't actually have a definition yet. We'll come back to that. So other things that are a part of this language, number one is that int is actually just going to be an alias for int32. So kind of like C should have done from the very start, but didn't due to historical reasons. We're going to have built-in fixed types, fixed width types. So there's going to be int8, it's going to be int16. I guess I'll put this on one line. int8, int16, int32, int64, and we'll also have uint8, uint16, uint32, uint64, and I think maybe optionally we'll also have an int128 size for now. Same thing with this. To be honest, actually, I'm not entirely sure having the kind of int uint differentiation is 100% worthwhile. I'm also kind of thinking that maybe we'll just have a general like integral type, in which case we would not have uint, we would just have int. And then if we wanted the specific sign variants, we'd call like sint or something. But, you know, there's discussions about whether or not the data type itself should be signed or whether or not the operation, for example, you do like signed addition or unsigned addition, etc., should be the way that you distinguish between int and signed and unsigned. But for the time being, just to get this thing off the ground, I guess we'll go with the classic int uint split, and then maybe in the future we'll change it. Floating point types, we'll have a float32 type, a float64 type, and I want to have float16 as well. If worse comes to worse, we'll have to emulate float16, or this can just be optional. But I think, especially going forward, there's going to be many CPUs coming out soon with co-pros. Well, they're not co-processors, but with floating point units that will have the half size. So we'll deal with that. And just to move the order of this, so int is just going to be an alias for int32. And in the same vein, uint is going to be an alias for uint32. And float will be an alias for float32. And I also wanted to have a byte type, which will essentially be an alias for, well, actually a few different types. A byte 8, that's going to be your typical like 8-bit byte, 16-bit byte, and then a 32-bit byte, and then a 64-bit byte. Whoops. And then of course, for the alias, this will just be byte 32. Byte 8, sorry. I think that's what most people expect when they expect byte to be, with no qualifier on the side. Now, as for string types, I've thought about this a lot, to be honest. And here's what I'm thinking about. So in C, you have C-style strings. And what a C-style string is that you have, you know, you have your array of characters. Like you might have A, B, C, and then at the end you have ASCII 0, right? To terminate. You have the null terminator at the end to say when you're at the end. But on the other side of the world, you have Pascal style strings. And a Pascal style string is when you have Well, first, the string can only be 256 characters long because you have the very first byte be the length of the byte. So this is a number between 0 and 255. And then, well, I guess in this case, you wouldn't be able to have a zero length string because that'd be illegal. There's no the empty string. Well, I guess that's not true, is it? Anyway, the point is that you would have a value between 0 and 255 as the length of the string, and then you would have your characters laid out like this. And the reason why Pascal strings are useful is because in well, you always want to know the length of the string. Usually, if it's a C style string, there's really no choice but to either pass the length of the string separately from the string or to um, use stringlen and calculate the length of the string when it's needed. And I mean, that may have had its advantages back when CPUs were a lot less technologically advanced. However, certainly, especially in the way that I write code, I almost always need to have the length of the string be a separate data member for structs and things like this. And I definitely need when you're doing things like string concatenation or doing things with SIMD and whatnot, it's always helpful to have the length of the string be there in a known location, which is why Pascal style strings are preferable. However, strings should be bigger than 256 characters long or 255 if it's like this. So the only other thing to do is that if you had a string like this, then slots, if you think of it like an array, then slots like str 0, maybe str 1, str 2, and str 3. This, and then from str 4 and onwards, then this would be uh, a Pascal style string that also has the a 32-bit length member. So the string could at most be 4 gigabytes long. And of course, why would you stop there? Why would you not just have an arbitrary length string or go up to 64-bit? So that way you would have many terabytes of length. And the problem with having a string like this is that now you're trying to read the string as though it's or the first 4 characters as though it's an integer. And for storage, it becomes a really big problem because this, if you just naively store the bytes of the string in any order, then these are going to be potentially unaligned. And so, like, you might have 4 bytes here, but if the bytes begin at like 0x, say 41, and then go up to 0x 45, some CPUs are not going to be able to access the length of the string without some sort of performance penalty. And that's simply unacceptable. So I'm not entirely sure how we're going to do this. I've thought about other things. For example, and my keyboard is disconnected. Hang on, guys, 1 second while I get back my pointing devices. Okay, there we go. So I'm not entirely sure how I want to have the strings laid out. One of the other things that I was thinking about is that we could have a struct like a string 8 like this, and then what this would be is it would be like we would have the struct be like u in 8, and this would be length, and then here you would have a pointer to the string char 8. I guess I haven't talked about character types either. Let's come back to character types in 1 second, just to finish off my thought about the string. We could have a string 8, a pointer to the string be like this, and then we would have the actual data of the string, or I guess text we call it, be laid out like this. So whenever you declare a string to in your source code, you would actually be creating something binary compatible with this on the stack, and then you would use this as though it were like the string itself. But that could be a little annoying. Alternatively, I was thinking maybe this could be inline, like this, like a flexible array member. I should add that arrays are a part of the type in this language, not part of the variable like it is in C. So we could have something like this with a flexible array member. So that way you actually just have like a pointer. Every string would just be the pointer. So you would never have a string 8 itself. You would only ever have a pointer to the string. Like this. I'm not entirely sure how I feel about this either. I don't quite like this. Um, Alternatively, we could have it that there's just no string type. And whenever you make a string, like if you just say, uh, I'll use C++ syntax right now. If I just have a string like this, auto s equals, ABC, then this is not going to devolve into a pointer. Instead, what this will be is it will be an inline buffer of length 3 of char8s, like this. And so you never actually have a string that's stored away in the text of the program, in the text section of the program. Instead, every time that you use a string, you are just stack allocating a string onto the local call stack, and then whenever you wanted to pass the string around, at that point, you the programmer have the power to say whether or not you want it to be the type, like you want to pass a char array of size 3, or if you wanted to say throw away the type, throw away the bounds of the array and have it be like this, or if you wanted to have it be a variable length array, at least from the perspective of the user. And we'll talk about all of this more as we go forward. I can see talking just even about the semantics of the language will take a lot of time, but the structure of the language will come out the more that we code up the compiler for it. Now, for character types, which is, I suppose, maybe the last thing that we'll talk about today, uh, you know, C++ introduced char8 underscore t, and this is absolutely an abomination. Like, you should not have a standard type built in have an underscore t as the as the suffix of the type. And I understand why they did it. They did it because they didn't want to conflict with other user code, which is already um, hash defined or type def char8. But my god, this is ugly. So we're not going to do that, obviously. Char8, this is going to be an 8-bit wide unsigned character type. There's no signed character types. Everything's going to be unsigned. And then the idea of having char8 is that this would be kind of when you see char8, you should think to yourself that it's a UTF-8 encoding. And then char16, I think you can see where I'm going to go with this. Well, not 26. A 16-bit unsigned character, and this when you see char16, you should think UTF-16. Although UTF-16 is basically extinct nowadays in 2025. So I don't expect to see this be widely used anywhere. But char32, I think, would be a bit more because this would be, UTF-32. And there is no UTF-64, but just for completeness, we may as well have char64, and this would be a 64-bit. So if one day they ever decide to create an encoding for UTF-64 bits, then we're prepared for it. And I don't know if we'll ever have need for char 128, but if we did, then we would also have this be an optional type as well. So it's optional. Now, similar to my other aliases, which is here, the alias for char, if you just write char by itself, this is an alias for char8, which I think is what everyone would expect, since this would be the easiest to interoperate with C with. And also, UTF-8 dominates basically all text. Even this source file itself is UTF-8 encoded. So that's all I have to say about chars. Now, for the reason, where's my struct from before? I think I got rid of it by accident. So if we had our example of like the string 8 thing again, then this would be like I'm not would it mean that the length of the string is max 8 bits, or is it that it's that the underlying character type is UTF-8? Like, it's ambiguous, right? We don't know, or I haven't decided. So That's why I'm a little hesitant about having a built-in string type. And also, it's not like it's not like there's one canonical string type anyway. Depending on the situation, you may have different string types, as you can already see by having different character types. So I guess we're just gonna have to chalk this up to not being fully decided yet, but we'll get to it eventually. All right, cool. Um, so that's a lot of introduction um, to the language. We probably won't get around to writing any actual code today, but I suppose one more thing, which is kind of evident from the code that I've already written, is that we somehow have that a variable length array is attached to a pointer for a character. Like, what's going on here? So I guess I'll just talk about the type ordering. So, in C and C++, right? If you have an int I, then if you wanted to make this an array, then you would stick the array thing here, and then you would like have an initializer for it, right? But for various reasons, to do with type decay and all of this kind of stuff, basically having the array type be a part of the variable is not a good idea, or maybe it's at least not desirable for this language. I want the type to be attached to the underlying element type. So I is a 3-element array of integers. But also, I really want this language to have just exceptional metaprogramming facilities. So I'm not going to have it. So I don't want to have the type be on the left-hand side of the variable, because this makes metaprogramming essentially ridiculous. If you had some sort of complicated expression where like the type of some variable depends on like a previously declared thing, then this becomes extremely difficult to reason with. Also, the rest of the language kind of reads left to right. So you have the thing which declares what the entity is. So main is a function main. Um, like I had before, we have like a struct foo. So we have the struct foo. Um, things like this. Like the thing comes first, and then the name of the thing. So I don't want to have the types be like this as well. So what I'm actually going to do for the language is have, I think, order be the thing which introduces a variable for a local scope. And the reason for order is because the original meaning in C and C++ for order was an automatic variable, a variable that would be stack allocated and freed essentially based on the compiler going through the call stack and popping stack frames off of the program stack. But C++ reused this for type inference because C is an old language and C++ couldn't innovate that well. But I actually want to bring this back. So what I would like this to be would be, again, following in the vein of, say, Pascal, or something like this. And I think other languages have kind of done the same thing now, where if you wanted to have the full declaration for a variable like this, you would have it be like this, where you have I is an automatic variable and its type is int3. But depending on the way that you initialize it, we also want the compiler to be able to infer what this would be. So I also want to be able to write this where we can put the type next to the initializer, and then the compiler should be able to infer that I is a 3-element array. And depending on, again, this is just being cute at this point, if you don't put the bounds here, then you can put the bounds there. Then it would infer the bounds from the initializer. This is also in C and C++. So that I don't think is very surprising. But the reason why I want to have this form of variable introduction, not something like var, maybe not something like let, uh, maybe not something like const, is that I also want to be able to say local I like this. And what this would be is the equivalent of, say, a static int I or whatever, where now I would now belong to the function main. So every time you would enter main, even though main by definition is only entered and exited once, the point still stands that this would be a variable that's scoped to main rather than scoped. All of these variables are scoped to main. This would persist just like a local static variable in C and C++, where the storage for main I would actually exist not inside of the stack frame itself, but inside of say the BSS section of the executable. So I want to be able to do something like that. Local. Also, I wanted this local to refer to thread local, and if I wanted this to be, say, scope to the whole program itself, independent of any single thread, then I would also want to be able to stick the keyword global here. And global introduces a global variable that is global to the program, but not global to any calling function. So there's like two levels of scoping going on here. One level is the visibility for each thread of execution, and then there's one level of visibility for the actual like lexical scoping. Lexical scoping, if you're not aware, is basically scoping within a block of code. So these open and close braces are a block of code, and if I had like another block here, then foo would not be available outside of here because its lifetime, its scope of visibility ends at the right brace. Things that Python doesn't have, but that you wish it did have. So that's why I want this to be order. Now, as for constantness itself, constantness should, especially const and volatile, there's two levels. There's two kinds of const and volatile. There's a thing called bottom const and top level const, which is a mouthful, and I'm not going to talk about it directly in depth here, but just suffice to say that if you want this to be a constant variable, then you can just put the const there. And yes, I'm deciding that const should belong on the left of the specifier, or whatever this is, the storage class. So you would have like a const local main, a const global, not being on the inside like this. I'm not sure if this will create any problems. And then you could also put volatile here like this. I'm not sure, and this could go in any order, by the way. I'm not sure if having like these type, what would these be, modifiers? I'm not sure if having them be on the left side of the storage class is a problem, but for the time being, we're going to go with it being on the left side so that it reads like it's English. Const volatile global, const volatile global. I like this. So this is a very short introduction to the language, and we're going to be visiting this a whole lot more going forward. But thank you for watching, and I look forward to seeing how this is going to evolve. I really am. So yeah, stick around for the journey, and I'll catch you in the next time. Have a great one.